Welcome to part 3 of lecture 2 for nuclear forensics. This is the third part of the lecture on radiochemistry in nuclear forensics. The readings for part 3 of lecture 2, same chapter, chapter 2, physical basis of nuclear forensics analysis in the nuclear forensics analysis textbook. Part 3 will cover the fission process. The types of decays that we'll discuss within the course are listed here. Alpha decay, which we've already discussed, occurs among the heaviest elements. An example here is radium-226 that decays by an alpha that makes radon-220 and then energy. So energy is a common component of every alpha decay, and of every particle decay. This energy is actually the conversion of mass into energy. So E equals mc squared. Beta minus, in this case, a neutron is converted into a proton, so it moves up the periodic table. A beta particle, which is an electron, an antineutrino, and energy are produced. Positron decay, so these are in neutron deficient nuclides, where a proton is converted into a neutron, so it moves down the periodic table. A positron, which is the anti-particle of an electron, so it's the antimatter particle of an electron, and a neutrino are produced along with energy. Electron capture, where an isotope will capture one of its orbital electrons, it will use that, it will convert a proton into a neutron, so move down the periodic table, gives off a neutrino and energy. And then a final type of decay is spontaneous fission, where an isotope will spontaneously break into two components. An example here is californium-252 going to an isotope of xenon, an isotope of ruthenium, and then some neutrons, and of course with energy produced. These aren't the only decays. There are other more exotic decays that we'll discuss in the course, but these are the primary decays that are dominant in the chart of the nuclides. From the last decay we discussed, fission, one thing that's produced are the fission products. And the fission products, as we showed earlier, there's xenon, ruthenium, but you can get a probabilistic distribution of fission products as shown here for, in the green, uranium-233, in the red for uranium-235, and in the blue here for plutonium-239. See that there's a light peak and a heavy peak. There's these two variations that are shown. We're going to learn that the fission product distribution is dominated by the production of an isotope with a mass of 132, because that has two interesting nuclear properties associated with it. And we see here that this heavy fragment is pretty consistent regardless of what isotope undergoes fission, but the light fragment changes. So the uranium-233 is lighter, the uranium-235 is a little bit more, and the plutonium-239 is a little bit more, a little bit heavier. We can also see the influence of neutron energy. Now again, this is admittedly a log scale, but as we see, as the neutron energy increases, this valley area on the fission product distribution curve decreases. So there are two things going on that can change information about fission. One is the material that's undergoing the fission. We see a fission product distribution change. And then two is the energy of the neutron can also have an influence on the fission product distribution change. And here to note, if you wanted to identify which was the fuel, which fuel produced these isotopes, imagine if you looked at a ratio of zirconium to technetium, uranium-233, high amount of zirconium, low amount of technetium. The red uranium-235, about equal amounts zirconium, technetium, and plutonium-239, low amount of zirconium, high amount of technetium. Photon emission is observed through two routes in radiochemistry. One is through gamma decay, where an excited nuclear state de-excites by emission of a photon. So this can occur when a radioactive isotope decays to a daughter. It may not decay to the ground state directly. It may decay to an excited nuclear state. That nuclear state often has a lifetime on the order of nanoseconds to picoseconds. However, something that is metastable has a much longer lifetime. It can be hours, can even be years. For instance, technetium-99m is on the order of 6 hours. And it will stay in this excited state, decay by emission of a photon. Now, X-rays are also photon emission, but that's from the electron level. So it's not from the nucleus itself. And I'm sure you've seen this in previous courses. But a lower energy, a lower orbital electron is removed. Electrons from the higher occupancy occupy that space, and a photon is emitted with that change. You can also get X-rays from deacceleration of high energy electrons, and you can also get electron transitions from the inner orbitals. So you get a number of these changes occurring, producing these X-rays. One can produce X-rays by bombarding of metal with high energy electrons. You can have synchrotron light sources. You can have radioactive sources. So you can have a number of different sources that are used to produce these X-rays. The chart of the nuclides provides a bulk of the information we're going to use in the course on the isotopes. Initially, information on the chemical elements are given. For instance, as shown here, you can get the atomic mass, the average cross-section for each element. There's also nuclide information. So for any given isotope, you can see the spin and parity. So for instance, shown here, boron 8 is 2 plus, carbon 12, it's blank, that's because it's 0 plus. Spin and parity 0 plus for even nuclides, so they don't even list those. Carbon 13 is 1/-, so that's 1/2 minus carbon 13 NMR. You can get information on fission yield, we'll show that. You can also get information for stable isotopes, for instance, isotopic abundance, reaction cross sections, and mass. All the gray elements, all the gray isotopes here are stable, so the data that's provided here is the relative isotopic abundance. So as you see, lithium-6 is 7.59% of the lithium is lithium-6, where the remainder is lithium-7. For radioactive isotopes, data that is provided includes half-life, the modes of the decay and their energies, the beta disintegration energies, the isomeric states. There's information on natural decay series and reaction cross-sections. A key utilization of the chart of the nuclides is understanding isotope decay. From the legend on the chart of the nuclides, you'll see this little figure where it says the origin nucleus, and anything that comes with the word out, that has to do with a decay. In means that if I hit this nucleus with an alpha particle, this would form. If I hit it with a proton, this isotope would form. If we look at decay, if I emit an alpha particle, it goes from the original down diagonally 2. If a beta minus comes out, it moves up diagonally 1. And if a positron, or it decays by positron emission or by electron capture, it goes down diagonally. So let's take a look at an example of the area of the chart of the nuclides. If we look at something like plutonium-235, this symbol here is electron capture. So plutonium-235 decays, if I follow here, goes this way, and it decays to neptunium-235. It's going down because it's taking an excess proton and converting it to a neutron. If I have something such as protactinium-235, it decays by this beta minus, which is here, and it takes an extra neutron and converts it to a proton, so it moves up to uranium-235. And then if I have something like plutonium-238, it decays by alpha. There's a little alpha here. The original nucleus alpha out, so it goes down 2. And this plutonium-238 kicks out an alpha and makes uranium-234. So it's a loss of 2 protons and 2 neutrons, so it goes down by 2 protons and over by 2 neutrons. So it's a total mass loss of 4, but going down 2 rows. And you can use the chart of the nuclides to understand all sorts of decays and nuclear reactions. For instance, one is the formation of this isotope, plutonium-238, which will describe its uses. It's used in space exploration as a heat source to produce electricity in spacecraft. And we'll discuss this and other isotopes during the course. The legend of the chart of the nuclides is useful for demonstrating the information that's provided in the database. The chemical elements given, so for instance as shown here for lithium, the atomic mass on the carbon-12 scale, there was a time when oxygen-16 was used as the scale, the name of the element, and then the thermal neutron absorption cross-section in Barnes for the element, followed by the integral cross-section also in Barnes. For a stable isotope, which is listed in gray, stable or very long-lived isotopes are in gray. You get the symbol, the mass, the atomic percent abundance, the ground states of even Z, the ground state spin and parity, as we stated earlier. Even nuclei are 0+. The thermal cross-section in Barnes leading to isomeric and ground state, and the resonance cross-section in Barnes, isomeric and ground state. This triangle here means that this isotope is produced from the fission, and this is the mass of the isotope. We will describe cross-section in more detail when we discuss nuclear. Moving on to the radioactive isotopes. Their mass and symbol shown here. It's non-gray. The color has to do with the half-life of the isotope, which can be seen in the legend. Spin and parity, again, 5/ minus is 5/2 minus. The half-life, 10.98 days. The modes of decay followed by their energy with MeV for alpha and beta, KeV for gammas. So this decays with an energy of 0.805 MeV beta. So beta is listed here. The gamma is 91.1 KeV. The cross-section information and the beta disintegration energy. As you see, the beta disintegration energy is a little bit higher than the beta decay energy, so some of the energy is going elsewhere, possibly to a gamma decay. And then again, this triangle says that it is a fission product from the slow neutron fission of uranium-235. Okay, here are some naturally occurring radioactive isotopes. The gray, again, it's stable, but these are long-lived, so it's long-lived or stable. This black bar, this is the indicator that it's naturally occurring. So lanthanum-138, a spin of 5+. This is the abundance, so 0.09% of lanthanum is this isotope. The half-life is 1 × 10 to the 11th years. So 1 × 10 to the 11th years, if Earth is 4.5 billion years old, the half-life is longer than the age of the planet. Again, modes of decay, E, this E here is electron capture, beta minus, gamma, cross-section information, and isotopic mass. And this square, as opposed to the triangle, means that it's a shielded fission product. It's still a fission product, but we'll discuss what shielded means. It means that there's a stable isotope in front of it, so it doesn't get fed along the 138 decay chain. Other information is shown here. This is a historic symbol. So lead-210 It's also known as radium-D. It was the fourth daughter down from the decay of radium. So historically, you've got this name radium-D. That'll be shown. You'll see some boxes that are split. So this is a metastable state, ground state, so metastable state, spin and parity, half-life, decay modes, ground state, spin and parity. This is stable, so this is the atomic abundance. And then two isomeric states that are both radioactive, so tellurium-131. The metastable state, spin and parity, 11 halves minus. Ground state, 3 halves plus. The half-life of each state, and then the other data as we discussed. We also stated that the fission yields for a given isobar can be identified in the chart of the nuclides. Here's an example. It says fission yields of uranium-233 and plutonium-239. The 239 is in parentheses. So for a given isobar, for instance, this 102, this 2.4 is for the fission yield of uranium-233. Plutonium-239 is in parentheses. So 1.6% of the time, it produces, when plutonium fissions, it produces a fission product with a mass of 102. Uranium-233, when it fissions through thermal neutrons, 2.4% of the time, it produces a fission product with a mass of 102. And I do want you to note that if you look at the plutonium values, they go from 5.4, they peak at around 7, and they start going back down to 2.2%. So something that's close to 7%, 6% is a very high fission yield. There's similar data for fissions from uranium-235. You see it's just on this side. And again, these numbers, they go from 0.03%. They can go even lower. And they shoot up all the way up to about 6.2%, going from an A of 125 to 140. Okay, should be able to identify questions like how many stable isotopes of nickel are there? Go to nickel, count the number of gray boxes. What's the mass and isotopic abundance of a given isotope? For instance, strontium-84. The spin and parity of an isotope. The decay modes, so we talked with bismuth-212. What are the isotopes of a given series? The front part of the chart of the nuclides has information on the decay series. What are the half-lives of given isotopes? Lutetium-176, terbium-176. How is plutonium-238 produced? How do you make plutonium-239 from uranium-238? We've actually discussed these in the previous lecture, but you should be able to look at the chart of the nuclides and figure that out. Which actinide isotopes are likely to undergo neutron-induced fission? Those with large fission cross sections. So when they capture a neutron, they undergo fission. It's the sigma F. As an example, you can look at the data for uranium-235 or plutonium-239. And which isotopes are likely to undergo alpha decay? The heavier isotopes. So as an example, what is the half-life of tellurium-130? If I look at this, if I look at the, let's see, it's gray. That usually means it's stable, but it's actually extremely long-lived. It's 6 times 10 to the 20th years. And what's the cross-section, what cross-section data is provided for tellurium-130? Well, I've got this thermal and resonance making both the metastable and ground state, metastable and ground state. So I have 4 different reaction cross-sections to consider, because if a neutron, depending upon the energy, if it hits tellurium-130, the neutron energy for thermal neutrons are described here. It can make this metastable or this ground state, and more energetic neutron can make this metastable or this ground state. The table of the isotopes is another a compendium of data that's used in the course, and it contains much more detailed information on each isotope. There's mass decay schemes, mass excesses, particle separations energy, population reactions, gamma transition energies and their intensities, decay levels, and a drawing of the structure. Right now, this is just an introduction to this information. Later in the course, we'll go over this information in much more detail. One can utilize the table of the isotopes in the PDF form as shown here. Opening it up, you would see this page. You can click on the summary scheme index. You would get a table that's shown here. This would allow you to pick any summary of isotopes with a given mass. The mass parabola, for instance, we'll select A of 60. We would click on that. It would pull up information. It would go to this mass parabola as shown here. So these are the isotopes with an A of 60, some fundamental information. For instance, we'd want to look at cobalt 60. We can get more detailed information on cobalt 60 by clicking this. It would bring us to this page, which would give us information on the mass excess, the neutron separation energy, the proton separation energy, the Q value. These are all these terms that we'll define later. Reactions on how they're produced, then branching levels. If I clicked on this value here, it would bring me to here. And this is my decay scheme. And this shows how cobalt 60 with a 5.2714 year half-life, a spin and parity of 5/2 plus, decays to nickel. And as we see that 99.925% of the time it decays to this excited state of nickel. And then that excited state, 99.9% decays to this state, and then 99.98% of the time it decays down to the ground state. So what this would show for cobalt 60, we would get two photons from the gamma decay, one at 1173 keV and another one is 1332 keV. So the gammas are related to the decay of the cobalt. Each one of these states have a half-life on the order of picoseconds, and they decay rapidly to this stable nickel 60. We'll go over this information in more detail throughout the course. Right now it's just kind of introduction for the data that's available in the table of the isotopes. The readings for alpha decay are covered in Chapter 3 of Nuclear and Radiochemistry and Chapter 7 of Modern Nuclear Chemistry. This lecture is going to cover energetics of alpha decay, in other words, the energy related to the decays. We're going to get information from the theory of alpha decay as it's developed between energetics and half-lives. We're going to introduce a term called hindrance factors. We're also going to talk about heavy particle radioactivity. In other words, the emission of a charged particle larger than the helium nucleus. We'll introduce the concept that some isotopes have a very, very small branching of a decay of something like carbon-12. And then we'll talk about proton decay. There's a range on the chart of the nuclides, the proton drip line, and we'll discuss the emission of protons from isotopes. As we presented in our very first lecture on the history of modern nuclear physics, Ernest Rutherford and his team identified a positively charged particle being emitted from the nucleus. The helium-4 nucleus was based on observed emission bands. From this point, it was clear that a particle of 2 protons, 2 neutrons was coming out of the nucleus. Now, the energetics of alpha decay, their energies range from 2 to 9 MeV. Originally, they were thought to be monoenergetic. However, fine structure was discovered where the alpha decay energies can vary for a given isotope. And as we'll see, what this means is that alpha decay, when it goes to a daughter state, can decay to different levels in the daughter nucleus. Those energy levels differences are based on the differences on the alpha decay. So you can get information on the energy level differences, and those will often be accompanied by gamma emissions. So For instance, if an alpha decays to a energetic daughter state, that'll be accompanied by a gamma emission that will also be a measurement of that energetic state. And our general trend that we have for alpha decay, as we discussed earlier, is that a parent decays to a daughter. It loses 2 protons. The A changes by 4 because 2 neutrons are also emitted. They're emitted as this alpha particle, and we have this Q value. An example of an isotope that undergoes alpha decay is shown here, seaborgium-263. It decays, it loses 2 protons, 2 neutrons, so it goes to rutherfordium. The A reduces by 4, so it goes from 263 to 259. And there's a helium nucleus that's also emitted as the alpha particle. The energy, this Q value, we're going to find is really the sum of the alpha energy and the recoiling nucleus energy. And as we have already discussed, the Q value can be found through calculations or databases. Here's an example of an alpha decay spectrum for the decay of thorium-228. We see that there's a few different alpha decay energies observed, and I want to point out that this is log counts versus channel number. The channel number is directly correlated with energy. So we see that there is one peak that dominates, but a few peaks that can be observed at relatively low intensities. This relates to the decay scheme where bulk of the thorium-228 decays to the ground state of the radium-224. There are certain transitions that decay to higher level states of the daughter. There'll be less alpha energy, and they're accompanied by gamma decay. And the sum of the gamma and the alpha is equal to the energy from the alpha decay. So the alpha decay energies can vary for the same isotope, and we know that when we look at the chart of the nuclides, we have different alpha decay energies listed for a given isotope. There are over 350 alpha-emitting nuclei, and as I showed here, these alpha decay energies can be used to develop decay schemes. Fundamentally, all nuclei that are greater than 150 mass are thermodynamically unstable against alpha emission. That means they have a positive Q value. However, for many isotopes, this positive Q value is extremely small. It means that alpha decay is unlikely. So you generally see alpha with isotopes that are greater than a mass of 210. This isn't completely true. As we see here, their energy ranges from about 2 MeV to almost 12 MeV, where neodymium-144 is a very low energy alpha emitter in the lanthanides. Polonium-212 metastable is a very high energy. We're also going to see a correlation between half-life and decay energy, where the neodymium half-life is almost 10 to the 30th times longer than the polonium-212. And what we're going to find out is that, generally speaking, the shorter the half-life, the higher the alpha decay energy. And as is shown in the figure, we're also going to see where the binding energy, the alpha particle in the nucleus, is negative, alpha decay can occur. Another example of decay scheme, which you should be able to interpret, is shown here for the decay of americium-241. Americium-241 is known to have the photon, the gamma decay, at around 60 keV, shown here. The yield for this transition is around 36%. So 36% of the time this photon is observed. One can look at the data from the decay of americium-241, the 5/2 state, the ground state of the neptunium-237 daughters, 5/2 plus. That's a parity shift. There's the higher probabilities actually from the 5/2 state to this 5/2 state, which has an 85.5% transition. That is the 59.6 or 59.5 keV. That's the high transition, which is shown here, that this photon decays around 36% of the time. So the remainder of the transition must be photonless, but you can also see the transition values for this alpha decay. This has the as far as the hindrance factor, closest to 1, so it's the least hindered transition. The readings for Lecture 5 are Chapter 3 from Nuclear Radiochemistry and Chapter 8 from Modern Nuclear Chemistry. This chapter is going to cover the neutrino hypothesis. We're going to talk about spectral shape and what information can be derived from that. We're going to introduce something called Curie plots, which is a way of evaluating data to understand what sort of transitions occur. We're going to talk about equations that are used to derive the beta decay rate constants. We can use this information, since a rate constant can be measured, to understand some of the properties of the isotope undergoing decay. We're going to discuss selection rules, which are based upon the spin and parity change from the parent to the daughter state. Often the daughter state may be an excited nuclear state. Then we're going to talk about different types of transitions. Okay, the majority of radioactive nuclei are outside the range of alpha decay. Beta decay is a dominant form of decay for radioactive isotopes. It was the second particle that was found from uranium decay, hence beta. It's a negative particle. It has a distribution of energies. Unlike alpha, where you would see peaks, beta decay energies would be a distribution. There's also another particle that's necessary to balance the spin, because there's a parent, daughter, and electron. You need to account for a half integer spin somewhere. This is part of the driving factor for the neutrino hypothesis. In beta decay, the total mass remains unchanged, the A remains unchanged, but Z changes. For beta decay, electron capture, and positron decay, we get different changes in the Z. For beta decay, beta minus, where an electron is emitted, a neutron is converted to a proton. For electron capture and beta decay, positron decay, a proton is converted into a neutron. So for beta decay, elements move up the periodic table. Electron capture and positron decay, they move down the periodic table. As we can see, there's examples of, this is beta minus decay, electron capture. Beta minus decay, we're increasing the neutron number, A remains the same. Electron capture, we're decreasing the neutron number, A remains the same. And positron decay, we're decreasing the neutron number, A remains the same. The half-lives for beta decays are from a few milliseconds to 10 to the 14th years. You can see that this is a little bit different than the range for alpha decay. On a subatomic level, we could think of beta decay involving a few mechanisms. For instance, here's a neutron that's composed of 1 up, 2 down quarks. It gets converted into a proton, where one of these down quarks gets converted to an up quark with the emission of some particles, the electron, and the antineutrino. Similar to alpha decay, there's systematic variations with beta decay energy and half-life. This is shown by the mass parabola here, where we see that there's this larger energy change as we go from more unstable to more stable beta isotopes. However, unlike alpha decay with the Geiger-Nuttall equation, there's not as strong a relationship, this linear relationship, as what's observed with alpha decay. And what we're going to see is that beta decay half-lives really depend upon variations in spin and parity. Now, there are some trends that we can observe for beta stable nuclei. We look at a mass parabola for these odd A135. For most odd A isotopes, there's one beta stable nuclei. And if we look here, this is the barium-135, which is the most stable, sits at the bottom of this mass parabola. However, for even A, you can have up to 3 beta stable nuclei, and you can evaluate this by inspection from the chart of the nuclides. Some odd nuclei near the stability valley, for example, copper-64, can decay in both directions. As we see with copper-64, it has a beta minus and a beta plus positron emission. So both these form even nuclei. That's one of the reasons that you can drive this stability. And also, as we already discussed in the previous slide, beta particle energy is not discrete. There's a continuum of energy. And as we look here, you can find an electron emitted from the nucleus from a range of energies, and the same thing with the positron emitted from the nucleus for this copper-64 decay. This is unlike alpha decay, where you get very discrete energies. In closing out beta decay, we'll add one more beta decay method, the double beta decay. In this case, an isotope will emit two beta particles simultaneously during its decay. These tend to have very long half-life. Examples are listed here: the tellurium 130, selenium 82, germanium 76, molybdenum 100 also goes through this route. And that's what's seen here. This germanium, if it went through a single beta decay, would have to gain energy. It can lose energy if it skips this arsenic step and goes straight to the selenium. Now these have very long half-life, and it's also possible to have neutrino-less double beta decay, where either the neutrinos annihilate each other or they're absorbed by a nucleon. Now another branch of beta decay is a beta delayed decay. So nuclei far from stability can populate unbound states that lead to direct nucleon emission. And what this is, where you have a beta decay which is followed by neutron emission, so a beta delayed neutron. These are important for nuclear reactors. About 1% of the neutrons that are produced in fission are actually these beta delayed neutron emission. And we'll discuss this more when we talk about fission. The readings for this lecture are Modern Nuclear Chemistry, Chapter 9, and Nuclear and Radiochemistry, Chapter 3. This lecture is going to be in two parts. The first part is going to cover energetics related to gamma decay, the types of gamma decays, transition probabilities, what percentage of the time a gamma occurs. We'll also discuss internal conversion and angular correlation of gamma emission. In other words, if you could align the nucleus, certain nuclei properties would dictate that certain gamma lines will emit in defined angles. So gamma decay is the emission of a photon during the de-excitation of a nucleus. There are a wide range of energies and different yields from virtually 0 to 100%. We've already discussed isomeric states, and here's an example of an isomeric state, zinc 69M, where it has an excited nuclear state. So an isomer, as we discussed earlier, are two different configurations of the same isotope. They have different total angular momenta and different energies, right? The spin and parity of the ground state and the isomeric state are different. And they have different energies, one being the ground state, so the decay from a ground state to a daughter would have different energy from the decay of an isomeric state to the daughter. And since they're at different spin and parities, for instance, this excited metastable zinc 69 has a spin and parity 9/2 plus, the ground state 1/2 minus, large spin difference, parity flip, highly forbidden, just like in beta decay. And we see that this metastable state can decay either by emission of a photon to the ground state, and that occurs 99.967% of the time. Then a small percentage of the time, it'll decay by beta directly to the daughter. And as you can imagine, it would most likely decay to different states through the beta decay from the ground state, since it's going from 9/2 plus. In this case, it goes to a 5/2 minus state, whereas for the ground state of the zinc 69, it's 1/2 minus. It primarily goes to the 3/2 minus ground state of the gallium. And this decay from metastable state to the ground state is called an isomeric transition. And gamma decay energies range from a few keV to many MeV. One of the things that we're interested in evaluating in gamma decay is we need to understand what percentage of the time does a gamma occur. And we'll go over this with an example with europium 152. We've already discussed this in class where we talked about reactions where gamma decay can be used as a way of determining the concentration or the activity of an isotope, and you have to know what percentage of the time this gamma occurs with the decay. With europium-152, there are many different gamma decays. And actually, if we look at the europium-152 here, we see that it actually decays by electron capture and beta decay. There's also some metastable states. These isomeric transitions also occur, which are shown here. We're going to ignore those for now. But let's focus on trying to evaluate the gamma decay from europium-152. It's complicated because there's two different routes. There's electron capture and this beta decay. So as an example, let's try to figure out what are the major gammas that would be expected from the decay of europium-152, and then the percentage of those times those gammas are going to occur for each decay. And if you go to the chart of the nuclides, you'll see that there's 3 gammas that are listed for europium-152 decay. They're shown here, the 121, 1400, and 340 keVs for the decay of europium-152. Now if we look at some table of the isotope data, and we can get percent yields and transitions for gamma decay from this data, we see here's europium-152 decaying by beta emission, going to gadolinium-152. And from the table of the isotopes, we know, the chart of the nuclides, we know that there are 3 main gamma decays. And if we explore the data as we've shown for in the table of the isotopes, we can find the gamma decay for this 344 keV. So when europium-152 decays to the gadolinium-152, it goes to this excited state. This excited state is 344 keV above the ground state. It decays, and the percentage of the time, well, we have to find the percentage of the time which each decay, we multiply this number, 127.5, by 0.2085. We get that, so for every decay, there's a certain percentage that will show this gamma line, and we can find that information. As we see, we need to convert this data to percentage by multiplying by this factor. If you remember, we talked about this with the table of the isotopes for other data. Now we've evaluated one of the gamma lines, so there's still 2 of these 3 most common gamma lines for europium-152 decay we'd like to evaluate. If we look at the data for the 121.8 keV, we see that the data, the percentage is 1,362 times 0.02087. That decay is from this excited state of europium to this excited state of the samarium 152. So this is decaying by electron capture. Now the final data we need is for this 1408. The data that we can find from the table of the isotopes is listed here. So 1,000 times this number gives us the percentage. And the 1408 is actually shown on another decay scheme. If you see this decay scheme, goes up to 1371. If we wanted to go to 1408, we'd definitely have to get that, at least that excited above the ground state. So as you can see, for the europium-152, there's a lot of extra data that could make the evaluation and determination of the percentage of the decays a little bit less than straightforward. Another route to find these gamma decays, a little bit more straightforward method, is to search for them on these websites that are listed here. Both these sites here access the same databases. And what you need to do is go to these web pages. You can enter the element either by Z or by the symbol and the isotope, and data will come out such as what's shown here. You can also, if you have an Android, there's a browser that's available, and this is from the IAEA. I've put the link for that browser here, so you can also download that on your Android browser. So as opposed to the method with the table of the isotopes where you need to look at the data for each decay route, so electron capture and beta decay. With these databases, all you need to do is put in the isotope that you're interested in finding the gamma intensities for, and it'll provide the gamma intensities. And we'll look at these. So for instance, with the europium-152 example that we've gone through, here's the data for 121.8 keV. And what I wanted to point out is that there's two values for the decay of 121.8. And you can see that one of these values is for the metastable state and one's for the ground state. So we're interested in europium-152 from the ground state, so make sure you select the ground state data, which is here. And as you can see, that percentage is 28.58%. So 28.58% of the time, when europium-152 decays, you'll see a gamma at 121.8 keV. The next example is for 1408 keV, which is shown here. This is fairly straightforward, and we see that the data is 21%. And then finally, the last photo peak that we were looking at was the 344.3 keV, and again we have two of the exact same values. We see that one is from the metastable state, one's from the ground state. We're interested in the ground state, and we see that that value is 26.5. So we make sure we select that one. We have 26.5. And these values are much easier to find. Now the table that I'm showing here is actually just a smaller version of the entire data that you'll get for the gammas from europium-152. But as you can see, compared to the table of the isotope data, to find these percentages for the gamma intensities, this is a much more straightforward method. When nuclei decay by alpha or beta processes, the transition from the parent to the daughter state can leave the daughter in an excited nuclear state. And that's what we've been discussing when we talk about gamma decay. So that's the de-excitation of this daughter state. And if it emits this electromagnetic radiation, a photon, we call that gamma decay. However, there are other routes that are accessible for this de-excitation. If the de-excitation is from a very high energy state, generally well above 1 MeV, a proton-electron pair can be created, so pair production can also occur. There's also a route, and this is particularly dependent upon the spin and parity between the excited and the ground state, where internal conversions from the interactions between the nucleus and the atomic electrons can occur. So this is internal conversion electrons, where atomic electrons are emitted. The energy of their emission is based upon the difference between the nuclear excited state and the binding energy of the electron.
The readings for this lecture are Chapter 11 from Modern Nuclear Chemistry and Chapter 3 from Radiochemistry. The lecture covers a general overview of fission. We'll discuss the energetics related to fission. We'll see that energy from fission is much greater than the other decay processes we've discussed. We'll talk about the probability of a fission process occurring. We've already touched on this through the cross-section. We saw that certain isotopes have a high cross-section in terms of fission from absorption of a thermal neutron. We'll discuss that. We'll talk about fission product distributions, including total kinetic energy release, the mass distribution, and charge distribution. We'll talk about how fission has a role in nuclear reactors. It's the basis of the power generation from reactors. We'll also talk about a process where the isotope decays through a delayed neutron emission, which can induce fission. So we'll introduce delayed neutron isotopes from the fission process. And then we'll end this lecture talking about fission that's not induced from a neutron but proton-induced fission.
Overview of the fission process provided here, where an isotope, such as uranium-235, which has a relatively high thermal cross-section, thermal neutron capture cross-section for the fission process. In this case, uranium-235 absorbs a neutron, goes into an excited state. That excited state has two routes of de-excitation. It can decay by emission of a photon, going back to the ground state of uranium-236, or this uranium-236 can then fission, resulting in two fission products with some neutrons. And we'll discuss the fission products, the neutron emissions, and the probabilities associated with this process, along with the energetics in this lecture. Nuclear fission was discovered by Otto Hahn, Fritz Strassmann, and Lisa Meitner, and here's a picture of Lisa Meitner, back in 1938. They demonstrated that neutron irradiation of uranium resulted in some lower elements such as barium and lanthanum. They were able to perform chemical separation and showed that these fission products were indeed lower elements. They were able to induce fission in this uranium due to the odd number of neutrons. When the uranium, as we showed on the previous page, when the uranium-235 absorbed a neutron, that neutron that was absorbed paired with the unpaired neutron in the uranium nucleus, and that had additional energy, this pairing energy. That pairing energy wound up inducing fission. So odd N isotopes, heavy odd N isotopes, can undergo fission. In 1940, Georgy Flerov, who's pictured here, he was a Soviet scientist, reported that uranium-238 underwent spontaneous fission. So it fissioned on its own as basically another route of decay. Uranium-238 spontaneous fission half-life is around 10 to the 16th years. Remember, the half-life for that isotope is 4.5 times 10 to the 9th years. So the spontaneous fission half-life is much longer than the alpha decay half-life. Through investigations, several other spontaneous fission isotopes were found, and these partial fission half-lives can be anywhere from nanoseconds to 2 times 10 to the 17th year. So the partial fission half-life for uranium-238 is actually rather long. In addition to this neutron-induced fission, this thermal neutron-induced fission, fission can also occur if enough energy is supplied by the particle, and the particle has to overcome the Coulomb barrier. So a fast neutron with extra energy, can induce fission. That's what's shown here. Here's the neutron energy versus the fission cross-section. And we see for uranium-238, once we get up to 1 MeV, we start to have an increase in the fission cross-section. A proton can also induce fission. We'll discuss this at the end of the lecture. As we've already said with Georgy Flerov's work on spontaneous fission, that's fundamentally similar to alpha decay, where we get tunneling through a barrier. We've already discussed that this thermal neutron can induce fission from pairing of unpaired neutrons. That pairing produces energy, and that energy goes into the nucleus, which can be useful for inducing the fission. So nuclides with odd number of neutrons can be fissioned by thermal neutrons with large cross-sections, as this is shown here for uranium-238, where we see the fission cross-section high at low energies. And this follows a 1 over the frequency law for low energies. And these sharp resonances that we see in the middle between 1 times 10 to the first, 1 times 10 to the second, EV, those are called resonance energies. Those are the high resonance peaks for, in this case, the fission of uranium-235. We can demonstrate some of the energetics involved in these neutron pairing energies from Q-value calculations. So as we see here, we can have a reaction where we take an isotope, add a neutron, we get A plus 1 plus E, or the Q value. In the case that we see here, for uranium-235. The Q values are shown here. So for E, we would have the 235 plus a neutron minus uranium-236. So the 235 uranium, the Q values listed here. The neutron and the 236, that's equal to 6.5 MeV. For uranium-238, the data is shown here. So here's our Q value for mass excess uranium-238, mass excess uranium-239, mass excess for the neutron, giving us a Q value of 4.8 MeV. And then for uranium-233, the mass excesses are shown here. Again, this is the uranium-233, the neutron, and the uranium-234. You see the difference is that for the isotope that does not undergo fission from thermal neutrons, uranium-238, the Q value is 4.8 MeV. While for the isotopes that do undergo fission, both those Q values are above 6.5 MeV. It just happens that fission requires about, the fission barrier is about between 5 and 6 MeV. So that pairing energy provides enough energy to have the isotope overcome the fission barrier and experience fission. In the fission process, the fission products of the isotopes that we're most familiar with, uranium and plutonium, undergo an asymmetric mass distribution. And that asymmetric mass distribution is shown here. And this is for uranium-233, uranium-235 in red, and then plutonium-239 in blue. We see that there's a high peak, which is consistent. That mass doesn't tend to change for the different isotopes. This lower peak, we see that the peak increases with A. We have a mass distribution ratio of high to low of about 1.4 for uranium and plutonium. And these peaks, as we've discussed earlier, they're due to shell effects from the magic numbers. The peak is close to 132, which is a doubly magic 50 proton, 82 neutron, so that'd be tin 132. Symmetric fission is suppressed by a couple orders of magnitude relative to asymmetric fission. And this is all due to shell effects. In nuclear reactions, this can also occur. And the fission will compete with evaporation of nucleons in the region of high atomic numbers. So in other words, if you make an isotope from a nuclear reaction, it can undergo fission once it's formed as opposed to de-excitation by, for instance, emitting neutrons. We'll discuss this a little bit more when we talk about nuclear reactions. So as we've seen, the location of the heavy peak pretty much remains constant for the uranium isotopes and the plutonium-239. We see the lighter peak increasing. We can also see an influence of neutron energy, as what's seen here. This is for the 235 uranium fission yield with difference between thermal neutrons and 14 MeV neutrons. The obvious change is that as we increase the energy, this middle section, the yield goes up. What we're seeing is that we're kind of washing out some of the shell effects with higher energy. As we've already seen for uranium-233, uranium-235, and plutonium-239, the fission yield distribution actually varies with the fissile isotope. With the previous isotopes we mentioned, the uranium and plutonium isotopes, that fission yield distribution was rather small. But we can imagine, as what's shown here, as I start to increase the mass of the fissioning nucleus, the heavy curve remains constant and the light continues to increase. We can imagine eventually that particularly if we get at a close where Z is equal to 50. So Z being equal, where Z would be equal to 100, so that the fissioning isotopes would have a Z of 50, which is here. Fermium's a Z of 100. You can imagine that here we'd start getting symmetric fission. So if we look at fermium, as the mass of this fissioning system increases, the location of the heavy fission peak will start to coalesce with the light fission peak, and we can see areas on this curve where we're plotting N, the number of neutrons, against the mass of the fission fragments for the different, Z is plotted here. These are the different isotopes. We can see that those in the circles here are all symmetric. So we can definitely understand that the fission distribution is actually a function of, we've already shown it's the energy, but also the fissile isotope that's undergoing fission. Another aspect of fission products is how they are distributed. We've already talked about the yields being different, but even within a yield for a given isobar, for instance here the data is for A of 141, we have yields that can be either for specific isotopes, those are the independent fission yields, or the data that we see in the chart of the nuclides, the cumulative fission yields. For the most part, we've been working with the cumulative fission yields, which is an integration of all the independent fission yields for a given isobar. As we can see, the independent yields need to be determined for specific nuclides. These can be difficult to determine, especially with radionuclides fission products that are relatively short-lived. The data for both the independent and cumulative fission yields can be found at this web page listed here. You can find that you'll see that there's actually a relatively smaller amount of independent fission yields available. So the difference between the independent fission yields are shown here, where you have the dots on the line, and the cumulative fission yield is just the integration. And the cumulative fission yield, those are the data points that are available to us in the chart of the nuclides. We've previously described the distribution of fission products as a function of isotope. Now let's evaluate what actually happens with the nucleus as fissioning occurs. This is shown at the bottom of the figure, where the nucleus undergoes a change and eventually reaches a point where it's no longer stable. Imagine if we have charges, protons build up into the semicircular aspects of this nucleus. That charge eventually overcomes the adhesion due to nucleon-nucleon interactions. This is called the saddle point. And the rate of change of Coulomb energy is equal to the rate of change of nuclear surface energy at this point. And this induces that instability which drives the breakup of the nucleus. Beyond this point, we have fission. We have the scission point, where the nucleus divides into two fragments. The high charge in each fragment accelerates the particles away from each other, and we get about 90% of the final kinetic energy within a very short period of time, 10 to the minus 21 seconds.
The reason these delayed neutrons are important has to do with the fact that how fast the fission process is. About 1/10 of a millisecond is needed for a neutron from fission to react. So fission occurs, that neutron is born, that neutron then reacts with another isotope. One needs to have somewhat tight control on this, because even if you went for a tenth of a percent of an increase per generation, and you would have a 10% increase in 10 milliseconds. So you still need 100, you would basically need 100 generations for that, but it happens so quickly that 10 milliseconds, you could quickly add 10% more energy, 10% more heat to a reactor without this control. So these delayed neutrons, they all have half-lives much greater than 0.1 milliseconds. So that allows even this small fraction a means of having a little bit more control over the fission process. Now, we mentioned that for uranium-235, about 0.75% of the neutrons are delayed. And for uranium-233, it's about 0.25%, and same thing for plutonium-239. This means in some regards, uranium-235 is a better fuel for reactors, just as an example in regard to these delayed neutrons. Now, fission products also produce, they also have another influence on fission. This is, you can call it kind of a positive influence on fission. It gives off some neutrons. But there are some fission products that influence reactors because they absorb neutrons. In an example, the production of xenon-135 fission product has this isotope has a very large neutron capture cross section, 3 × 10⁶ barns. Buildup of this isotope in reactors can actually poison the reactors and shut down the process. In regards to the fact that the buildup of the xenon-135 means that this isotope then increases, and with the increase of that value, those isotopes are capturing more and more neutrons because of its cross-section.
Some more detail on neutrons and fission in reactors are presented here, where we see that the probable neutron energy is a little under an MeV, while the average energy is about 2 MeV. This is actually used in fast reactors, since 2 MeV neutrons are certainly high enough to fission non-fissile isotopes like uranium-235. The only thing you would need to do is construct a reactor where, for a fast reactor, where the neutrons are not moderated or slowed down. That would mean high Z reflector and coolant, which is not high Z. So they often use sodium as a coolant, or even lead and bismuth. Thermal reactors need to slow down the neutrons, so they'll use water, for example, as a coolant. Anything with a lot of protons, a lot of hydrogen, graphite, carbon, that can be used to slow down neutrons. And one thing, as we discussed in the previous slide, that the power of a reactor is proportional to the number of available neutrons. The neutrons come from the fission process that creates the energy, so the number of neutrons available is a rough measurement of the number of fissions that occurred. There's a factor K, which is a multiplication factor. It's the ratio of fissions from one generation to the next. And here we've plotted multiplication factors as a function of burnup on this slide here, or as another K effective term as a function of years. And one thing they would like to do in reactor systems is have a K effective which is fairly constant over time. Once you get a K effective below 1, you are no longer able to use that as fuel. In fact, you want a K effective really of 1. You want the ratio of fissions from one generation to the next to be nice and steady. So they actually configure the reactor material, put things like burnable poisons into the core. Burnable poison is just an isotope that will absorb the neutrons and eventually be used up through the fission process. And here's an example of those K effective terms. As you see that they vary around 1 for both these figures. Something else that occurs in the fission process is damage. The very fact that these particles are being emitted damage materials and fuel within reactors. The fission process itself, the fission products recoil about 10 microns in UO2, and there's a very high local temperature, almost 3,000 degrees C in 10 nanometer diameter within the fuel. Two of the types of irradiations that can, the damage that can occur from the radiation, one is swelling, which is shown here. There's a cube. Swelling is where the axes of each side of the cube increases. And then there's something called creep, where there's no volume change, but shape change. Both these types of damage can occur in reactors. So there's actually a good deal of new research focused on trying to find materials that are impervious to swelling and creep as a function of neutron damage. The energetics of the fission process, and that's what drives nuclear fission, but it's also something that we can use to evaluate which isotopes will fission and which ones won't. Fundamentally, any nucleus with an A greater than 100 can split into two approximately equal size with resulting energy. However, why do we only see fission at about 230? Because the separation of a nucleus is hindered by the Coulomb barrier. You could treat this barrier as penetration, what the particles would have to overcome in order to form two particles from a nucleus. So if we could figure out the energy from fission and compare that to the Coulomb barrier, we could evaluate the difference and find out where this fission is possible. So we would actually have to have the fission overcome the Coulomb barrier. It just turns out around uranium, both these quantities have values close to 200 MeV. The Coulomb barrier is close to 200 MeV. Fissioning is close to 200 MeV. And once the fission energy is above the Coulomb barrier, this event can occur.
So we should start by discussing the definition of radiochemistry. There's a few different definitions people use. One could be the chemistry of radioactive isotopes and elements, utilization of nuclear properties in evaluating and understanding chemistry, and one that I like is the intersection of the chart of the nuclides and the periodic table. I prefer this one because it shows that the chart of the nuclides are nuclear properties, periodic table of chemical properties, and as a radiochemist you transition back and forth between nuclear properties and chemical properties. So some of the things that we should understand when we talk about radiochemistry, let's start, since we want to talk about the nucleus and nuclear properties, let's start with that. The nucleus we can always describe as the number of Z protons and N number of neutrons in a nucleus. The diameter of the nucleus is about 10 to the minus 14 meters. And electron interactions with the nucleus, that's going to be the basis of chemical properties. Electrons are, those orbitals are on the order of 10 to the minus 10 meters. So the bulk of the radius and volume of an atom is composed of electrons, but the bulk of the mass, the small area, is occupied in the nucleus. And electrons, they can be excited, they can get into higher energy orbitals, they can undergo ionization. These binding energies of electrons can affect ionization. That changes some of the chemical properties, so different oxidation states. This will come into play more when we talk about the actinides, where there's multiple oxidation states. And that has to do with the fact that electrons are being loaded up into those electron orbitals, and the energy differences between the different orbitals are very small. So some of the terms that we have for atoms within radiochemistry, we've already discussed isotopes. So an isotope is the same Z, so the same proton number and different neutron numbers. An isobar, where we have the same A, the sum of the protons and neutrons. So as an isotope undergoes beta decay, it converts a neutron into a proton. So the sum, the A, remains the same. An isotone, that's the same number of neutrons but different number of protons. This is used to help identify how the neutrons and the protons have properties within the nucleus. And then something we've already mentioned, the isomer. So technetium-99m, that little M state, and it's a nucleus in an excited nuclear state. And the one way that we can describe a certain isotope is to have, as shown here, a chemical symbol with A, Z, the proton number, and possibly the neutron number listed here. Another term that we've described is the half-life. And the half-life is the amount of time it takes for half of a radioactive material to disappear. So for instance, if one has some iodine-131 and you measured that it was 25
milligrams. How long would it take it to go from 25 to 12.5 milligrams, to 6.2 milligrams, to 3.1 milligrams? Each one of these is cutting down by a half. It's first order decay. There's actually a fundamental relationship that's shown here where the number of, in this case, atoms, but if I know the number of atoms, I know the mass at a given time is equal to the amount initial times e to the minus lambda t. Lambda, the decay constant, is just equal to log 2, the natural log of 2, divided by the half-life. Now, if this time is in seconds, your half-life needs to be in seconds. If this time is in minutes, your half-life needs to be in minutes. In this first-order decay, this half-life term is fundamental in radioactive decay. Again, this is an equation that we will see frequently in the equations that we've discussed can be used to help define some of the terms that we're already using. We've already discussed half-life. That's the time it takes for half of something to decay away. We've seen a few of these curves, the relationship if it's log or linear. The half-life, let's define it, it needs to decrease radionuclides by 50%. And there's a relationship between the half-life and the decay constant. If I took the general equation where the number of atoms at a given time t is equal to the number of atoms initial times e to the minus lambda t, I just looked at the ratio. So the time that it takes to get to a half is equal to e to the minus lambda t. So half is equal to e to the minus lambda t. Let's take the natural log of 1/2 is equal to minus lambda times the half-life, because that's the amount of time it takes for this relationship to occur. So, in 1 half-life, this ratio should be 0.5. And then log 2 is equal to lambda times the half-life. And the half-life is equal to log 2 divided by lambda, or lambda is equal to log 2 divided by the half-life, as we already defined. There can be large variations in half-lives for different isotopes. Short half-lives can be effectively measured. Imagine if I had something that had a half-life on the order of many minutes to hours. I could use a detector. I could sit and count the decay of that isotope if it was, 10 minutes, and I measured a sample every 30 seconds. If I measured the decay every 30 seconds, and I bin that, I could plot it on a line like I would have here, and I would get a decay constant. So something that's a short half-life, that's observable experimentally somewhere along this line, all I need to do is get some areas where I can get some change, some statistically significant changes, and I can generate the equation to derive the half-life. If it's a long half-life, and basically the rate isn't going to change over my measurement period, so imagine something with 10,000, 100,000 years, something like on the order of plutonium-239, around 20,000 years. This is based on the decay rate in the sample, so I need to know the total amount of a nuclide in the sample. So if I had some plutonium-239 and I weighed it, and I got N, and I got the activity of that N, well, I could solve for the decay constant, and then when I get the decay constant, I know that the decay constant is equal to log 2 divided by the half-life. I've measured the half-life. An example of doing something like this is with using a potassium salt. You could get potassium chloride. Potassium-40 is a naturally occurring radioactive isotope. One could put that on a gamma detector, look for the potassium-40, understand the efficiency of that potassium-40 peak on that detector in that geometry, and use that weighing the total amount of potassium chloride, knowing the fraction of potassium chloride that's potassium-40, calculate what the half-life is, and you can compare it to the measured value. So as opposed to discussing the half-life of a radionuclide, the amount of time it takes for half of that radionuclide to decay, I can also discuss an average lifetime of a radionuclide. So it's the sum of times of the existence of all atoms divided by the initial number of nuclides. So this average lifetime is equal to this equation here. And I can expand on this. It turns out to be 1 over the decay constant. 1 over the decay constant is equal to 1 over log 2 divided by the half-life. And it turns out that the average isotope has a lifetime on the order of 1.4 times the half-life. So the average lifetime is greater than half the half-life by this factor. And during some sort of time of initial activity, it's reduced to 1 over E of its initial activity. So I can understand the relationships between these two. But when would you want to know the average lifetime? Well, a lot of times it's important if I'm talking about dose, if I want to understand what's going to be the average dose that one would get. Then you would talk about the average lifetime. Or if I'm doing atom at a time chemistry, which is what I did as a graduate student, if I only have one atom in a solution, half-life doesn't really make sense. And what you talk about is the average lifetime. So what we would do, we'd measure the average lifetime, get an ensemble of atoms together, measuring the average lifetimes, then we can get a half-life from that. But if you think about it, what you're really doing, if an ensemble, a regular experiment where I can measure the half-life, is really having a large enough collection of atoms to measure these individual averages in an ensembled system that allows you to derive something like a half-life as opposed to just a lifetime. This is a summary slide of everything we discussed previously. This slide has the equations one should focus on. We've got a few equations. This n at a given t is equal to n initial e to the minus lambda t, where this is some sort of number of radionuclides, the decay constant, and time. It also works for activity or counts, right? Because they're both related to n, the number of atoms. It could work for mass. It can work for anything that you could connect. If you could talk about a concentration, how the concentration changes, as long as the volume remains the same, but you're decreasing the number of atoms. We also have activity equals lambda n. So the number of atoms times n is equal to activity. So this is becquerel, which is count per second, and curies, which is 3.7 times 10 to the 10th decays per second. So 3.7 times 10 to the 10th becquerels. We also have lifetime, which is the average lifetime of an atom is 1.443 times its half-life. And if you think about it from the decay, half the atoms should decay within the 1 half-life, but within 2 half-lives, 25% should be there. So the average atom's going to live a little bit longer than the half-life. And then finally, the error, where we have m is the number of counts, and this standard deviation is just equal to the square root of the number of counts. And we use this to determine how long we should perform an experiment to get a reasonable count rate so that the error generated from the counts isn't exceeding or driving the experimental error. And you can use some of the information we just discussed, for instance, calculate a decay constant. If I give you an isotope and you have the listed half-lives, I can calculate the decay constant in inverse time units. So if it's listed in days here, it would be inverse days. But usually we want the decay constant all in the same time unit. We tend to have seconds. So I can go here. If I have a half-life in days, I need to convert those days to seconds. If I have years, I need to convert those years to seconds. But as we see, the longer the half-life, the smaller the decay constant, because it's log 2 divided by the half-life. So as an example of the selenium-75, the half-life is 119.78 days. Log 2 divided by 119.78 days is equal to 5.79 times 10 to the minus 3 days. But if I want that in seconds, convert the days to hours, hours to seconds, and then I get the decay constant in seconds. Based upon some of the equations that we've reviewed, one should be able to answer some of the following questions. For instance, if you have 1 gram of selenium-72 initially, how much remains after 12 days? Well, the half-life is 8.5 days. The decay constant is log 2 divided by 8.5 days. The number initial times e to the minus lambda t. Well, this is nominally for atoms, but atoms, grams, they're completely linear relationship. So 1 gram times e to the minus lambda times t, 12 days, you get 0.376 grams. So if you started with 10,000 atoms of selenium-72, how many atoms would remain after 12 days? Well, after 12 days, it's 0.736, so 37.6% remain. So if I started out with 10,000 atoms, I'd have 3,760 atoms after 12 days. So these relationships are the same: mass, number of atoms, they're correlated.
Other examples of equations and reactions and decays you should be able to understand from this first lecture are shown here. So for instance, if you're given a certain isotope, arsenic-66, figure out how much of that isotope remains after a given time, half a second. So how would one do that? If just a percentage, well, use the equation where I put in n naught, that's my initial amount. N at time t is this n value here. I know that I want to figure out what that percentage is, or that ratio at the given conditions shown here. So half a second, get my decay constant. The half-life of this isotope is 95.6 milliseconds. Convert that to seconds. My decay constant is 7.25 inverse seconds. E to the minus 7.25 times half a second is equal to 0.0226. A percentage is 2.66, and that's equal 2.66 is equal to that ratio. That's after a little over 5 half-lives. So that shows that if you wait a number of half-lives, the radiation decays away effectively. And nominally, as a rule of thumb, you use between 7 and 10 half-lives before an isotope fundamentally disappears. As an example of that equation, how long would it take for 90% of a given isotope, in this case zinc-65, to decay? Well, let's use this equation again. However, we need to set up so that if we're talking about 90% of it decaying, the amount that remains is 10%. So you take 100 minus the percentage that you're interested in, and that will give you this ratio value, which I show us here. The half-life is 244 days. Let's just use the value in days. Log 2 divided by that, 244, shown here. I set up my equation, solve for t. T equals 810 days. So you can use this to estimate the time or calculate the time to get any sort of ratios, or calculate the ratios at any given time.
Let's make some examples with these equations. So a half-life calculation, let's use the number of atoms at a given time is equal to the number initial e to the minus lambda t. All right, so we'll utilize this in terms of activity. We have an initial count rate of 890 becquerel. After 180 minutes, the count rate was found to be 750 becquerel. What's the half-life of the isotope? Well, activity at given time is equal to activity initial e to the minus lambda t. Solve for lambda. We get to lambda, and it's in minutes because we're looking at minutes. We get a value, this value here is equal to 9.5 times 10 to the minus 4 minutes, inverse minutes is equal to lambda log 2, which is equal to log 2 divided by the half-life. So the half-life is equal to log 2 divided by this value, So the half-life is equal to 729.6 minutes. I could also ask you, okay, how would you describe the error in this study? Well, you need some information. If the count was 750 becquerel, well, you need to say how long was it counted and what was the efficiency of the detector. Ideally, you'd like to go somewhere between 1,000 and 10,000 counts. The previous example showed an example of calculating a short-lived isotope, something where you can look at change over a reasonable time. Well, let's take an example of something where the half-life is rather long. So we use activity equal lambda n, and the example is 150 milligrams, so 0.15 grams of curium-248, shown to have an alpha activity listed here, 0.636 millicuries. So what's the half-life? First of all, let's find the activity. I'm giving you the activity in millicuries. You'd like it to put into something like counts per second. So 0.636 times 10 to the minus 3 curies times 3.7 times 10 to the 10th counts or becquerels per curie, counts per second per curie, gives me my activity in counts per second. So 2.57 times 10 to the 7th becquerel. I need to find n. That's pretty straightforward. If I give you the mass and you have if I give you the mass and I know what the molecular weight is from curium-248, I have Avogadro's number. I can get the number of atoms, which is shown here. And now I set up my equation. And I use the activity equals lambda n, solve for lambda, put this in. I get lambda is equal to 6.46 times 10 to the minus 14th inverse seconds. Solve for the half-life, where lambda is equal to log 2 divided by the half-life. I get this equation, and I get my time unit in seconds because it's inverse seconds. So that is the one thing you need to be aware of, is that you got to keep your time units consistent whenever you do these calculations. Now, the time unit in seconds, that's not really helpful. 1 times 10 to the 13th seconds. So we convert that to minutes, hours, days, years. So the half-life of curium-248 is 3.4 times 10 to the 5th years. We can use, again, activity equals lambda n from an example where we actually do some counting. Let's say you've got a gamma detector, and at 60 keV, the efficiency is 15.5%. What is the expected gamma counts from 75 micromoles of americium-241? Well, I use this information here to get the gamma branch, which is for americium-241.
The gamma efficiency data shown here is from the table of the isotopes and the Lund University site. These data sets include information not only on gamma decay, but other decay routes, and we will describe these data sets in more detail later in the course.
The gamma branch at 60 keV, so 59 right over here, is, I multiply it by 1 times 10 to the minus 5. This is 3.56 times 10 to the 6, so it's 35.9% is my gamma branch.
Unlike the table of the isotope data, the gamma branching values from the Lund University website are already normalized, so the value here is 35.9, which is the same value from the table of the isotopes.
So I need to take my detector efficiency,
which in this example is measured to be 15.5%.
multiply it by the gamma branching. So in other words, for every time americium decays, 35.9% of the time this photon appears. When that photon appears, I only see it in the detector 15.5% of the time. Then I use my lambda n, That's equal to my counts. I put in my half-life.
Using the half-life of 432.7 years and normalizing that to seconds, where there's 3.16 times 10 to the 7th seconds per year, you get a half-life of 1.37 times 10 to the 10th seconds.
I get the seconds because remember I said the half-life needs to be at the same unit. It's given to you in years. I need to convert it to seconds. I use this seconds half-life to get the decay constant. So I want to find N. I tell you that there's 75 micromoles of the americium. It tells you how many atoms of americium are present. So activity equals lambda N, right, which is this term. Then I still need to multiply it by the gamma efficiency and then the detector efficiency. So activity equals lambda N times the gamma branching ratio times the detector efficiency. But if I put this sample in, I would expect to have 1.3 times 10 to the 8th count per seconds. That's way too many counts. You would saturate your detector. So what this tells you right away is that that concentration is way too high. We're talking orders of magnitude. You'd better go to 75 nanomoles or even picomoles. You can afford to have 1.28 times 10 to the second counts per second. So you have a lot of variability that you can build into the system. Also helps you understand what concentrations are suitable for doing measurements in your experiments. Another term that's often used in radiochemistry is specific activity. And this is the activity of a given amount of radionuclide. So suppose you use activity equals lambda N, but it really defines how much of a mass or a concentration or a given amount of a radionuclide gives off a certain activity. So the specific activity is listed here, SA of radium-226. We've already described that. So 1 gram of radium-226, the half-life here, we go through the calculation, is equal to 3.7 times 10 to the 10th becquerels. Everything is listed here. And this is the definition of a Curie. This shows the calculations that are done to demonstrate that radium-226 is indeed a Curie. And this is an example of a specific activity where a gram of radium is equal to 3.7 times 10 to the 10th becquerels. And you can imagine doing this for a gram of any isotope you're interested in.
The cross-section is used in equations to calculate reaction rates. You can think of the cross-section as the probability of a reaction
To occur.
and it's a term that we've already discussed.
The cross-section symbol is sigma, and some values for reactions with neutrons can be found in the chart of the nuclides.
For example, this tellurium-130, there's cross-sections that go from thermal neutron, resonance neutron, to the metastable state, and then thermal resonance to the ground state. These values are described within the chart of the nuclides. So it's a term we've already discussed, and it has a dimensioned area. It's 10 to the minus 24 centimeters squared is the value for the cross-section, which is called a barn. And barn value is strange unit, right? 10 to the minus 24 centimeters squared. Well, a nuclear radius is around 10 to the minus 14 meters squared. If I took the area pi r squared, I'd get a dimension that would be on the order of 10 to the minus 24 centimeters squared. Now this value originates from the probability of a reaction between a nucleus and a particle, and it's proportional to the physical cross-section of the area presented by the nucleus. This isn't completely true. For instance, with a charged particle, you have a Coulomb barrier to overcome. With slow neutrons, you have resonances that are based upon some quantum mechanical properties. Basically, a general trend would be that the reaction cross-section is going to be fundamentally proportional to the area that the particle can see from the nucleus. And this is really true. If you have fast particles, the cross-section is never greater than twice the geometric cross-section of the nucleus. Cross-sections for fast particles tend to be close to a barn. It also depends upon the exact reaction that you're looking at. And what we're going to see when we explore cross-sections is that we'll have some cross-sections which are close to a barn seem reasonable. And then some cross sections that are multiple barns, thousands of barns. So in essence, it's as if the nucleus expands. That's not what's really happening. Quantum mechanics comes into play, and you have wave function overlaps that increase the probability of reactions. So let's see how cross-section can be used in some reactions. The cross-sections that are in the chart of the nuclides are for neutron reactions, and the sigma that represents the cross-section will have a symbol next to it, a gamma or a F, gamma for just neutron capture, F for fission. We'll explain this in more detail when we discuss those different reactions. But there's also cross-sections for accelerator reactions. So in an accelerator reaction, a beam of particles strikes a thin target with a minimum beam attenuation. So the energy loss as the beam travels through the target can be neglected for this equation to be valid. And that's important because
for accelerator-based reactions, the cross-section is a function of the projectile energy. For a given reaction, the change in cross-section with energy is called an excitation function, and we will discuss this in more detail later in the course.
So we have these terms where we have the incident particles per unit time, a beam current. We have the number of
target atoms
per centimeter cubed. We have a target thickness in centimeters, so we see that we get an inverse centimeter unit here. And then we have the cross section, which is in centimeters squared. So we see that the area values get removed. For reactors, we use a different equation, and we assume that a particle,
in this case the neutron, has
a uniform flux, is impinging upon a target, and cross section
for a given reaction with the target isotope.
So we've got the rate of reactions, some sort of processes just over here, how many reactions are occurring per unit time, is equal to the cross section times the number of nuclei that are in the sample times the flux. So that's particles per centimeter squared per second. And this is a property, this flux is a property of the reactor. This target, that's the property of the target that you're putting in. And this is the cross section that one can find. Of course, if I had an unknown and I measured the rate of the reaction, the rate of the process, and I knew something about the reactor flux, and I knew the number of atoms that were in the target, I could figure out the cross-section. And if I had an unknown reactor and I wanted to measure its flux, I would put a target that's known in with a cross-section that's understood, measure
the reaction rate,
and I could evaluate the flux. So these equations provide us an opportunity to evaluate terms and processes in nuclear reactions. Those equations that I showed in the previous slide are fundamentally correct. However, we are neglecting an important consideration, and that's the decay of any isotopes that are produced while the production is ongoing. And we need to consider something a saturation factor.
In the previous slide, we discussed rates of formation. Another way of evaluating these rates of formation is shown here using this equation, where if the activity of an isotope is measured after the reactions to produce that isotope, and that activity is divided by this saturation factor, 1 minus e to the minus lambda t, that'll provide the rate of formation. And that should be the same rate of formation value as calculated from the equations on the previous slide. Since the measured activity divided by the saturation factor yields the isotope formation rate, one could evaluate cross-sections, fluxes, and target information using experimental data from an irradiation, as we discussed in the previous slide.
But let's think about what this saturation factor means. As one is producing an isotope, when it's made, it also has a probability of decaying.
If the isotope is stable, this probability is 0. Otherwise, it is based on the half-life.
So if you're producing an isotope that has a half-life of 100 years, and you're producing it in a reactor,
and that reaction takes an hour,
the probability that one of the atoms you made that has a half-life of 100 years decaying within that hour is pretty small. So we don't really need to include the saturation factor. However, if you're
irradiating a sample for an hour, and the half-life of the isotope that you're producing is 3 hours,
a measurable amount of that isotope may have decayed.
and you need to include this saturation factor.
Using the saturation factor, the number of product atoms produced is equal to the number of target atoms times the cross-section times the flux, as we discussed on the previous page, divided by the decay constant for the atom produced times the saturation factor, 1 minus e to the minus lambda t, where lambda is the decay constant for the isotope produced. If the number of product atoms are known, the activity can be found by multiplying the number of product atoms by the decay constant. And all we need to do is rearrange this equation.
The activity of 1 is equal to the initial amount of target times the cross-section times the flux, same equation as we used in the previous page, multiplied by 1 minus e to the minus lambda 1t. So this is the decay constant of the isotope that you're producing.
This term, 1 minus e to the minus lambda t, is called the saturation factor, and it
gives you an idea of where you're going to reach a maximum level. As one continues to irradiate, and if I look at the amount of half-lives of the daughter, and I compare that to the irradiation time, I reach a level where longer irradiations does not produce more material. This is because over here, as let's say within 1 half-life, it's fairly linear. Some of the atoms that have been produced have decayed because the atoms are being produced over this entire half-life time. So the ones that were initially produced at the very beginning of the reaction have a 50% probability of decaying, while those at the end have a very small probability of decaying. But as I increase this, more of the initial atoms have a probability of decaying because they're experiencing many half-lives. And you just reach a point around 7 half-lives where fundamentally reached an equilibrium that you're producing more from a reaction, but you're losing those atoms that were made earlier. So this tells you that if you're doing a production reaction, you should never go more than 7 half-lives of your isotope. So if I was making an isotope that was an hour, anything more than 7 half-lives is not worth it. In fact, you can make an argument that, well, the amount that I gain from 4 to 7 is pretty small. 3 to 7 is pretty small. From 2 to 7, I'm only gaining 25% more. So one could evaluate that. Is it really worth that extra time to produce a relatively small amount of material? So we have these saturation factors, and as a function of half-life, you can see what sort of percentage of the saturation you're reaching. Let's compare these two equations in two different scenarios. One where the irradiation time is short compared to the half-life, and one where the irradiation time is long compared to the half-life. So for our first example, let's use a reaction to make iron 59, this isotope, 44.5 day half-life, from iron 58. We'll add a neutron to the iron 58. It will absorb that neutron, give off a gamma, and make iron 59. It gives off the gamma because it makes an excited iron 59 state. That photon makes it decay to the ground state. So it's just a simple transition. And we see that as this N, gamma, iron 59. So target, projectile, reaction product, reaction product. Another way of writing it is shown here. We'll go over more detail about this reaction later in the course, how we this sort of nomenclature. But we can also write it as iron 58 plus a neutron goes to a photon plus iron 59. The cross section we can get right from the chart of the nuclides. It's 1.3. I write it here 1.3 times 10 to the minus 24 centimeters squared, because remember it's in Barnes, so this is in Barnes, and 10 to the minus 24 centimeters squared is our Barnes unit. So let's take our equation that we have here. We want to get N, right? We want to get the number of atoms that are sitting in the target. I state that there's 1 gram of iron. The molecular weight of iron is listed here. We use Avogadro's number. So now we've got the number of atoms of iron, and then I'm going to use this value because this is for iron. I didn't say any sort of enriched iron, I just said regular iron. And 0.282% of iron is iron 58, so I need to normalize it by that. And I get the number of targets as 3.04 times 10 to the 19th atoms. All right, so we've got our information. We've got our flux, which I provide here, a neutron flux. We've got the number of atoms, and we've got the cross section. So let's plug this information in to the equation. Flux, number of target atoms, cross sections. I get a rate of 3.95 times 10 to the 8th atoms per second. I say I want this irradiation for an hour. So there's 3,600 seconds in an hour. So from this, I get 1.4 times 10 to the 12th atoms of iron 59 are made in 1 hour. Now this reaction does not include the decay of any iron 59 that's during that hour of production. Let's include that by using the saturation factor. So the same terms that we used in this equation, we got to add something about the decay, so we got to bring in the decay constant. I provided the decay constant here, but it's just log 2 divided by the half-life, but this is all in seconds, so make sure if you were to do that yourself, you would convert days into seconds. So we use this equation. Let's plug in the terms. The number of iron 59 atoms that are made is equal to the number of target atoms times the cross-section times the flux divided by the decay constant times 1 minus e to the decay constant times the time. And that's where our time, that's the only place where the time really comes in. And this is basically providing a saturation factor. It says what percentage of the material is available. And what we get is a value that's shown here. We get 1.4 times 10 to the 12th atoms. We got 1.4 times 10 to the 12th atoms, and it says, you see, you need to go down to the 4th significant digit in order to see a difference. And as we would expect, this value would be less than this value. So this shows that you could use either equation if something is relatively long-lived. If you have a spreadsheet that's set up and you're inputting the data, it doesn't really matter which equation you use. They would both equally well describe the reactions. Let's consider a condition where the radiation is relatively long compared to the half-life. So let's take the formation of manganese 56 from manganese 55. Again, a neutron capture reaction. So manganese 55 captures a neutron, gives off a gamma, makes this manganese 56. The half-life of the manganese 56 is 2.6 hours. We'll do an hour irradiation. So when we say that the radiation is long compared to the half-life, doesn't necessarily need to be longer than the half-life. It just needs to be a good fraction of the half-life in order for the saturation to come into play. All right, so let's get some of the data. Our cross-section for the manganese 55. So remember, the manganese 55 is absorbing the neutron, so you need that cross-section, not the manganese 56 cross-section. We have our cross-section is 3.3 times 10 to the minus 24 centimeters squared. It's 13.3 times 10 to the minus 24 centimeters squared. The 13.3 Barnes value is listed here. Again, this is for thermal neutrons. You can assume I'm using a thermal neutron flux. This is for epithermal neutron flux or resonance energies, resonance neutron flux. If it's unclear in a question, you're free to use whichever one you want. I will try to specify, for instance, radiation from thermal neutrons. We have our data, right? We need to get the number of manganese targets. Said there's a gram of manganese. All of manganese is iron 55. The molecular weight of that all that manganese is all manganese is manganese 55. The molecular weight of that manganese 55 is listed here. So we have a way of calculating the number of manganese targets from 1 gram. That's sitting in the neutron flux. Let's use our equation. Let's input the terms. The rate is equal to the flux times the cross-section times the number of targets. We get a rate of 1.45 times 10 to the 12th atoms per second, 3,600 seconds in an hour. We get a value that we should make 5.24 times, or 5.25 times 10 to the 15th atoms of manganese 56 in an hour. Now remember, this equation does not count for decay. Let's consider decay. We use this equation where we have the saturation factor along with the decay constant. Let's plug those values in and let's solve. We get a distinctly different value. We get 4.6 times 10 to the 15th atoms. So this is a demonstration that if you are producing an isotope that's relatively short-lived, where the irradiation time is long compared to the half-life, you need to definitely include the saturation factor for accurate assessment of the amount of atoms that would be produced. We introduced this equation a few slides ago, where we can determine the formation rate based upon measured activity and this saturation factor. So let's look at the example from the manganese 56 that we provided in the previous slide. We've gone through how we determine this value. Our activity, if I know the number of atoms of manganese 56, the decay constant, right? So activity equals lambda n. I have that value. I get so many becquerels, so 3.4 times 10 to the 11th becquerels. That's my activity. I substitute the activity into 1 minus e to the minus lambda times the time, and I get a production rate. So this production rate includes it's the overall production rate, and it does include the decay as a function of the irradiation time.
Equations that show the production of isotopes from accelerators were also provided, and we're going to show an example of that using the production of astatine-211 based upon conditions that are used at the University of Washington. The equation that was used is shown here, and the components of this equation, as a reminder, include your beam current, which ultimately is particles per second, so it's the projectile particles hitting the target. And then target information, which includes the atom density, so atoms per centimeter cubed, times the target thickness, that'll get centimeters squared. And then we get the cross-section, which is shown here from experimental data. And this cross-section for this reaction is about 1,000 millibarns. So that's 1 barn. And we'll use that as the cross-section. And remember, that's in 10 to the minus 24 centimeters squared per barn. So the data that we need to accumulate to run this equation is the same if we go for the equation that does not have the saturation or the equation which does have the saturation. The only addition for the saturation equation is the inclusion of the decay constant. And again, just like the reactor example that we showed on the previous page, if we know the activity and divide that by the saturation factor, we will get the production rate. So for the production of astatine-211, which is used as a radiopharmaceutical, the reaction includes a bismuth target, a helium projectile, 2 neutrons come off, and the product nuclei astatine-211 is produced. The helium target is a monovalent helium beam, and at 30 MeV it has a beam current of 70 microamps for this accelerator. The unit ampere is used to convert the microamps to charges per second using the conversion that 1 ampere is equal to 6.24 times 10 to the 18th charges per second. And since the helium projectile is monovalent, one helium projectile is one charge. So from the 70 microamps, you multiply that by 6.42 times 10 to the 18th charges per second per amp, and you get 4.37 times 10 to the 14th particles impinging on the target per second. For the number of atoms per centimeter cubed, the target is metallic bismuth. Assuming 100% density of your target, use the density of bismuth, which is shown here to 9.7 grams per centimeter cubed. Convert that to atoms using the atomic mass of bismuth and Avogadro's number. You get 2.808 times 10 to the 22nd bismuth atoms per centimeter cubed. So that's the number of targets per centimeter cubed. The target thickness for this example will be 0.1 centimeter. So that's the value for X. For these calculations, the target information may be provided directly. For example, as opposed to providing the thickness and the density, one may be provided the number of atoms in the target or the mass of the target that is being bombarded. And the cross-section, again shown here, has a value of 1 barn. 1 barn is 1 times 10 to the minus 24 centimeter squared. Continuing with the example of the production of astatine-211, based upon the conditions used at the University of Washington, the decay constant for the astatine-211 isotope needs to be determined. The data from the chart of the nuclides show that the half-life is 7.21 hours for astatine-211. Converting that into the decay constant is simply log 2 divided by the half-life. Remember that the half-life should be converted into seconds, so it's 7.21 hours with 3,600 seconds per hour. You get a decay constant of 2.67 times 10 to the minus 5 inverse seconds. For this example, calculate the production of astatine-211 atoms for a 3-hour irradiation. Again, 3 hours, convert that into seconds. 10,800 seconds, set that as time t. So for the two examples, let's do the production. For no decay correction, the atoms of astatine-211 is equal to the equation we've shown before. And since it's a production rate that is not decay corrected, we'll just multiply it by the number of seconds for the irradiation. And we're going to set that equal to N1 as a comparison point. N1 is equal to particles per second times the atom density times the target thickness times the cross-section times the time. And those values are shown here with the particles per second, atom density, target thickness, cross-section from the previous slide, and the irradiation time provided above. One gets the production of 1.3 times 10 to the 16th atoms of astatine-211, and that's equal to 3.5 times 10 to the 11th becquerel, and that's simply found from activity equals lambda n. Comparison to the decay-corrected equation, which is shown here, substituting the terms and the addition of the decay constant. The equation terms are shown here using, again, the same terms as the non-saturated equation with the addition of the decay constant and the saturation term. One gets the production of 1.2 times 10 to the 6th atoms of astatine with an activity of 3 times 10 to the 11th becquerels. And we see that the decay correction shows that the amount of astatine produced is reduced since the irradiation is for 3 hours. The half-life of the astatine is 7.2 hours. They're on the same order. This is a demonstration that both equations can be used. However, the decay correction equation certainly is the suitable equation for this condition based upon the half-life of the produced isotope.
We now have an opportunity to take these equations to calculate growth and decay and use them to explore how we can determine the age of materials based upon naturally occurring radionuclides. So there are two sets of naturally occurring radionuclides, let's say primordial radionuclides, that have survived since they were first deposited on Earth. They tend to have a half-life of greater than 1 billion years. They also have decay products that are formed from these long-lived radionuclides. We saw the example of uranium-238, uranium-235, thorium-232 are also decay chains. And here's an example of potassium-40. And again, I wanted to point out from the chart of the nuclides, this black bar here designates that it's a naturally occurring radionuclide. In this case, long-lived. Potassium-40, any potassium-40 that was originally deposited on Earth 1 billion years ago has gone through on the order of 1 half-life. The age of the universe, nominally 4.5 billion years. The potassium-40 has gone through a half-life, but there's still a reasonable amount of material. Now, there's also shorter-lived radionuclides that are formed from continuous reactions with cosmic rays and with matter. So, for instance, tritium, carbon-14, beryllium-7. Here's the data from the chart of the nuclides for carbon-14. Its half-life is 5,000 years. Obviously, if any carbon-14 that was originally deposited on Earth during the formation 1 billion years ago is long since decayed. But these nuclear reactions, and for carbon-14, neutrons hitting nitrogen-14 produce a proton and carbon-14. And these reactions, there's also a reaction for producing carbon-12, but this reaction, as you can imagine, this is a neutron with sufficient energy to knock out a proton. This reaction occurs because the atmosphere is primarily nitrogen. Most of that is nitrogen-14, so this is our target. The neutrons are formed from cosmic rays coming in, forming these neutrons in nuclear reactions, and those neutrons then hitting the nitrogen-14, liberating a proton, and forming this carbon-14. Now, anthropogenic radionuclides have also been introduced, so radionuclides made by human activity. These are primarily actinides and fission products. They also include carbon-14 and tritium, and these have been introduced through weapons testing. All these radionuclides, particularly the naturally occurring ones, can be used to evaluate dating. However, if one is going to use carbon-14 or tritium, or anything that was introduced through anthropogenic activities, a normalization has to occur for accurate dating of these materials. So if we have a long-lived isotope that decays to some ground state or stable daughter or another long-lived daughter, we can use this as a clock to determine the age of something. And the clock is basically from this equation where the number of atoms at given time t is just equal to the number initial times e to the minus lambda t. So let's rearrange this equation and solve for t, and the equation becomes what is shown here, where it's equal to the natural log ratio of the initial and the number of atoms at time t, and the decay constant of what's decaying. Now, this doesn't really seem to help because it implies that we need to know the number of atoms at time 0. I can measure at time t. If I know what isotope is decaying, I've got the decay constant, I just don't know this value. We need to be able to determine what this time t is. And what we can say is that, well, the decay of the parent to the daughter is constant. And let's just say the total amount of daughter plus the total amount of parent at time t is equal to the initial amount of parent. And all we're saying is that we can determine the amount of the parent
At time 0.
So this n naught value based upon what we measure currently for the amount of daughter and the amount of parent present.
Where n naught is the same as p naught, the amount of parent isotope at time 0.
So we basically rearrange this. The amount of parent at time t equals the amount of parent that's initial times e to the minus lambda t. Let's rearrange this equation.
Solve for t.
And it becomes the amount of parent at time t, daughter at time t, and the decay constant. That's all we need to know to determine the date. So what we're saying at time 0, that there were no daughter atoms present. That all the daughter atoms are due to the decay of the parent, and that no daughter atoms were lost during this decay period. So there are a few conditions that are necessary so this relationship of all the parent at time 0 being described by the parent at time t and the daughter at time t. So let's consider how this could work. Imagine that there's a mineral, for instance, zircons, which are zirconium oxides, have a small amount of uranium embedded in them. One can evaluate these zircons, look at the amount of uranium-238, and the daughter that we're talking about in this case is lead-206. Now, if you look at the decay chain, which we explored earlier, that's not a direct decay. There are many decays, but fundamentally, if you look at the half-lives of the isotopes between uranium-238 and lead-206, most of them are relatively short-lived compared to the half-life of uranium-238. So in essence, we just can take the uranium-238 half-life as a decay directly to the lead-208. So what we need to assume is that there was no lead-206 present at time 0 in this zircon, that all the lead-206 that is there is due to the decay of uranium-238, and that no lead-206 was lost during the lifetime of this material. What you could do for lead, if you were to evaluate if there was other lead present, lead has other stable isotopes, you could determine how much lead there is. Look at, for instance, lead-208, how much of that was there. And if you don't see the lead-208, you're convinced that lead is only from this decay. Also, the isotopics of the lead will show you that information. Of course, if there's uranium-238 present in your sample, you're probably also going to have uranium-235, and those daughters will also need to be considered. So if we go through this, what is the age of the mineral? Substitute our terms into this equation. So it's the decay constant, log 2, divided by 4.5 billion years. The log of 1 plus the daughter and the parent.
Ratio.
And I said that the fraction is shown here, the ratio. So we can just take those values at time 0. The daughter is not present. At time t, that was providing this ratio, the daughter to the parent, it's 0.4. So this becomes the inverse of the decay constant times log of 1.4, and you get 2.2 billion years. And that's actually accurate time frame for some zircons, and this technique is actually used for dating older zircons. Again, we use this equation. This is our fundamental equation. All we need to know is the decay constant and the ratio of the parent and daughter today. Carbon-14 dating is a little bit different. Okay, this is based upon the uptake of carbon-14. Carbon-14, the half-life is 5,000 years. This is useful for this half-life of 5,000 years. What it implies is that an organism is taking in carbon. The ratio of carbon-14 to other carbon is constant. It's based upon the environmental uptake of that carbon. That organism is no longer taking up carbon upon its death, or it ceases that interaction. So the carbon-14 begins to decay. If I know the amount of carbon-14 in a certain amount of carbon at equilibrium at time 0, and I see how much carbon-14 there is per a unit mass of carbon at the current time, one could measure the sample age. We just rearrange the equation we used previously. 1 divided by the decay constant of carbon-14 times the log of the carbon-14 at equilibrium divided by the carbon-14 in the sample. So the equilibrium value is listed here. And what's the age? There's a wooden sample that's been found. It now has 0.15 becquerel per gram. This is 227 becquerel per kilogram, so we need to make it per gram, so it's 0.227 becquerel per gram. Let's rearrange these equations, and we get the natural log of 0.227 divided by 0.15, and we get 3,420 years. Carbon-14, 5,000 year half-life, is reasonable for doing carbon dating on that order, so thousands of years. There's actually another way that you can do carbon dating as opposed to looking at the radioactive decay. You can use a mass spec and count the number of carbon-14 atoms in a carbon sample. So you get that ratio, right? The activity is fundamentally using activity equals lambda n. I can get the number of atoms of carbon-14 per the number of atoms of total carbon. If I used a mass spec, I can actually count them. And you can go to actually lower detection limits. And that's one of the methods that is used today. And again, it's the same equation that we talked about previously, but now it's specialized for normalization of carbon-14 at equilibrium. And the equilibrium value shown here, again, this is listed in becquerel per kilogram. If your data is provided in grams, you need to change that normalization. These dating equations can also be varied to evaluate some conditions to understand the age of certain objects. So for instance, we can use an example as the Oklo reactor. This is provided on page 40 on the chart of the nuclide, some discussion of the Oklo reactor, and you can look it up online. But the Oklo reactor was a natural reactor that operated a few billion years ago. So we can use the dating
Equations
that we just provided to kind of get an idea of what would be a reasonable time for that natural reactor to have been fissioning. This was actually determined when uranium samples from an area were evaluated, and the uranium-235 concentration in those samples was found to be lower than expected. This lower amount of uranium-235 indicated that it had previously fissioned, and they also saw some evidence of some fission products. So it indicated that at one time, the configuration of this natural ore body was sufficient to create natural reactor. And you can read about the details of this. So let's figure out a route of rearranging these equations to determine what was the time that the Oklo reactor was operating. Let's use the amount of uranium-235 as an indicator. Today, 0.7% of uranium is 235. And if we look at a reactor with light water, with regular water, the uranium-235 needs to be at 3.5%. The half-life of uranium-235 is shorter than the half-life of uranium-238. So fundamentally, there's a clock set up that
if we know the uranium-235 to 238 isotopic ratio today, and we want the amount of uranium-235 to be 3.5% at time 0.
So let's compare the 235 to 238, and we'll call it this uranium ratio, and use our regular decay equation. So we need to just set up the ratios. So the ratio of uranium today is equal to the initial ratio times, we got to take the decay constants for the 235 and the 238, since we're using a ratio of 235 and 238. The time is equal, it's the same. Let's rearrange this equation so that the amount at time 0 is just equal e to the minus lambda 235 times t plus lambda 238 times t. So now we have everything we need to know to solve this equation. We just rearrange, we solve for time. We have the ratio at time t, the initial ratio. We know the decay constants. We rearrange this equation, and we get a value on the order of 2 billion years, which is actually pretty accurate. So again, we input the ratio from today, input the ratio that we know that's a condition for the reactor to operate, throw in the constants, calculate, and we get a reasonable value. And all this was done is just based upon understanding that a reactor needs about 3.5% of uranium-235 with natural light water in order for fission to occur. Now the data that I showed you is available, the mass excess data, and if I know the mass excess data, I can actually calculate Q values for a number of different reactions. One area where you can find this information, as I already mentioned, on the the table of the isotopes, you can get some of the Q value reactions. But there's also something that you can get on your phone, the IAEA, International Atomic Energy Agency isotope browser. Information on the isotope browser is available here from this web page, but you can download it from your Android or Apple-based applications. The IAEA isotope browser, it will include Q values, but also include information on energy of the decays, half-lives, decay modes, percentages, and other information that will be useful for the course. So I use the IAEA isotope browser all the time, and it's certainly a resource that you can use. So if you wanted to do Q value calculations of specific reactions, you don't necessarily have to go through and use the mass excesses as we just described. Mainly that information was presented so you understand where the data comes from. A lot of this compendium is already available. If you had the isotope browser, first thing you'd want to do is select the isotope you're interested in. So here is carbon-14 listed. You would then select Go, and that would bring you to this page. Here would be the information, carbon-14, the half-life, the spin imparity, and the decay mode, followed by the percentage or any sort of branching ratios. You would select this, and it would bring you over to the next page where it would have the information on carbon-14, would give you the references, gives you the number of protons, neutrons, spin imparity, the half-life, the parents, the decays, and it gives you these Q values. So you can calculate the Q alpha, the Q beta, the Q electron capture. These are neutron and proton separation energies. There's binding energies, masses, cross-section information. By moving around and exploring, you can find a lot of different information. So for instance, we know that carbon-14 decays by beta, and it has the energy in keV of that beta, along with the percentage, and then decay energy information. So there's lots of information on these isotopes. So for here, one of the first questions we asked, what's the Q value for the beta decay of carbon-14? You could use the isotope browser and got 156.476 keV.
When you have completed this lecture, please comment on the blog and respond to the Lecture 3 quiz. The lecture summary is provided here. Those terms and concepts that you should focus on from the lecture are shown here. The error in counting is an important term that was discussed, and it's simply the square root of the number of counts. This dictates conditions when one does work with radioactive material. There were a number of examples of utilization of equations of growth and decay. Examples include determining the number of atoms at time t from an initial amount of atoms using this equation, the activity from the number of atoms and the decay constant. This is a very fundamental equation, activity equals lambda n, and the relationship between half-life and the lifetime. This shows that the average lifetime for an atom is a little bit over the half-life. You should be able to calculate parent-daughter relationships. The full equation for the parent-daughter relationship is shown here, where the daughter atoms at a given time are a function of the amount of initial parent and any initial daughter that's present. There are relationships that can simplify this based upon the half-lives of the parents and the daughters. You should be able to do calculations for multiple progeny using programs and understand that the Bateman equation is used to do multiple progeny. However, you will not be asked to calculate the Bateman equation or develop programs or spreadsheets for doing the Bateman equation. You should understand branching decay, that isotopes can decay by more than one decay route. Often this is not the case, however, there are examples that were presented and that we'll discuss later in the course. You should be able to use the branching ratio for mixed decay to find the partial half-life of a given decay. So for instance, with bismuth-212, which decays by alpha and beta, the data shows a half-life for bismuth-212. You can use that to determine a decay constant for bismuth-212. However, the partial half-lives or the partial decay constants for the alpha decay and the beta decay are based upon the branching ratios. For isotope production, you should be able to use cross-sections for isotope productions and understand there are different equations for reactors and accelerators. And you should be able to include the saturation term that accounts for the decay of produced isotopes during production. Finally, this lecture discussed age dating using isotopes. You should be able to understand what are the necessary conditions for dating to be successful and what equations can be used for this, particularly the different equations that are used for carbon-14.